Professor Caudill here. We are on 63A, so we're given the density of the sun, which is 10 to the 3 kilograms per meters cubic. So we want to know the diameter. We have the density, now we want the diameter. Is what? So, you know the density, rho. Okay, so I should say rho of a celestial body. You want diameter, you can use volume relationship, volume. So we know volume of a sphere is roughly 4/3 pi r cubic. So density is meters over volume. Okay, so we do know the mass of the sun. So it's going to be 10 to the 3 kilograms. Then what the diameter? Diameter is 2 times pi. So we know the mass of the sun is 10 to the 30. And it's going to be 4/3 pi r cubed. So we want to solve for r. So it's going to be equals 10 to the 3 kilograms a meter. Okay, so we're going to get r cubed is about, let's say that's 10 to the 4. So let's say 10 to the -1. So we are going to take both sides times 1/3 power. So r is about 10 to -1/3 meters. Probably a pretty bad estimate. Let's move on. All right, 64. Mass of a virus. So we know, so what is, we know the diameter. Diameter of a virus. You find mass of an object with its diameter. Mass density. So we need okay, so mass is density times volume. Volume is 4/3 pi density over 2 cubed. Okay, so we know this, and we know this. Okay, so we do not know this. We do not know this, but we know this. So we need to know the density. What is density? I think it's mass over volume. Okay. So, like this doesn't make sense because I need mass to get the density. What other measurements might be useful givens for calculating the mass or density of a virus? Nucleic acid, virus, spectroscopy, concentration. Yeah, I don't know. I'm not really happy with the book. It's not either. I don't know. I don't think it's fair. It's being very fair with how much it's given. Floating point operation is a single arithmetic operation. Okay. So supercomputer does 10 to 17 beats per second. Human lifetime is 10 to the 9 seconds. Okay, so they want to know how many computes. So it's going to be 10 to the 26 computes. Pure human lifetime. Okay. All right. I think we move on. That section was just, I think, mostly was poorly phrased or not. Yeah, just poor questions, I think. Consider the equation 4,400 is 10. Okay, so they both have one significant figure. Okay, easy, 67. Suppose your bathroom scale reads your mass at 65 kilograms. Okay, so you're just going to take 65 times 0.03. So we're just going to say 10 to the 2 plus minus 10 to the 1, 10 to the 0. Yeah, there we go. there's your uncertainty. 68, a good quality measuring tape can be off by half a centimeter. What is percent uncertainty? Okay, so 20 centimeters, that's about 10 to the 1 centimeters, plus minus 0.5, that's about 10 to the 0. So what percent is that? So we're going to take 10 to the 1 times so 1, what's 1%? So that's 10 to the 0 times 1 is 10 to the 1, right? All right. $69. Okay, infant's pulse rate is 130 plus 5. That's right. Okay, so we have 1. So we have 10 to the 3 because no, it'd be 10 to the 2. 10 to the 2 plus 5 beats per minute. Okay, so uncertainty. That's about 5%. All right. Suppose that a person has an average heart of 72 beats a minute. How many beats does she have in 2 years? Okay, so beats a minute, that's about 10 to the 2 beats a minute. So we want to convert minutes to days. I'm sorry, we want to convert minutes to hours. So how many minutes are in an hour? Ten to the 2. Okay, how many hours are in a day? 10 to the 1. There's 24 hours in a day. It's about 10 to the 1. And 2 years, so times 10 times 365 times 10 to the 3 days in a year. Okay. 3 2. All right, so you're going to get 10 to the 4, 5, 10 to the 8. So times 2 beats in 2 years. Okay, 71. Can contains 3. Can contains 10 to the 3 milliliters of soda. How much is left after 3 to 8? Okay, so that's 10 to 3 minus 10 to 3 equals about 0. That's how much is left. So 72. State how many significant figures are proper in the results following. Okay, so we're taking 10 to the 2 times 10 to the 2 is about 10 to the 4. So it's about 1 significant figure. Oh, we're dividing it by 10 to the 2. So still going to be about 1 significant figure. 18, what is this? 10 to the 1 squared. It's about 10 to the 2. 1 significant figure. 10 to the negative 19 times 10 to the 3, 4. Alright, that's about 10 to the 5. With one significant figure. 73. How many significant figures are in the numbers 99 and 100? So that's 2 significant figures and 3 significant figures. Or I could say 1, because it's 1 times 10 to the 2. If the certainty in each number is 1, what is percent uncertainty? 0. What is a more meaningful way to express the accuracy of these numbers? I don't know what you're asking. Let's move on. If your speedometer has an uncertainty of 2 kilometers at 9 miles per hour, what is percent uncertainty? Okay, so we're going 10 to the 2 kilometers an hour plus minus 10 to the 0. So our percent certainty is about 0%, or we can probably say 1%. If the same certainty reaches at 6 kilometers hours, that's about the same. 75. Blood pressure, 10 to the 10 plus 2 Hgs. So it's 10 to the 2 plus minus 10 to the 0 Hgs. Percent certainty, it's about 1%. Millimeter Hgs. Assuming the same percent uncertainty, what is the certainty? 80. Oh, it's about the same. 76. Person measures his or her heart by counting the number of beats in 30 seconds. Okay, so you're getting 80 plus minus 2 over 60 plus minus 1 seconds. Okay, so that's about 4, 3, plus minus 1 beats a second. So that's about 25% uncertainty. Well, these would cancel out, so you would have 4/3. So you would have no uncertainty. 77. What is the area of a circle? What is the area of a circle? What is the area of a circle this length in diameter? Okay, so A is 2 pi r squared. So I feel like these are a little bit better to memorize when you're thinking in dimensions. Because, 2 pi r is the circumference. Pi d is the circumference. But r squared, that means it's 2 dimensions, so it has to be the area. So radius is d over 2. So it's saying we want radius is about 10 to the 0 divided by 2. It's about 10 to the 0. So let's see. 2 So what is it saying? It's saying about 6 times 10 to the 2, which is about 10 to the 3 cubic centimeters. Okay, 78. Determine the centimeters. Okay, so that has that has 3, 4 significant figures. B has 3, 5, 3, 3 has 4 significant figures. C has 1, 8 has 4, E has 4. Okay. 79. So bag 1 is 13.5 pound. Bag 2 is 10, yeah, 110 pound. What is the total weight? Total weight of the bags. In bags in pounds? Okay, so that's easy. So this is going to be 5/10. So we're going to have B1 plus B2 is 20. 3. 6/10 is 3/5. Okay. All right, so we want to know the force given 10 to the 2 kilograms times, what is this? 2, that's 10 to the negative 2. 10 to the negative 2 meters a second squared, right? Because that would be 2 times 10 to the negative 2. The force is about 10 to 0 newtons. Okay. Additional problems. All right, consider the equation y equals mt plus b. Y is length. Dimensions, SI units. Okay, so your M and B are constants, so they're dimensionless. M times T is going to be a time dimension in seconds. And B is going to be time dimension with no SI unit. Okay, easy enough. 81. Okay, I'm considering it. S is the length, T is the time. Okay, so S naught will be a length dimension with meters. V naught will be a time dimension in seconds. Well, V naught itself is dimensionless. It's a constant. So its SI unit would be nothing. A naught would be, looks like it's a constant, so it's no dimension, no SI unit. J naught, same thing. S naught, same thing. C, same thing. Okay, 82. Cars per hour has 5% uncertainty. So what is 5%? 5% uncertainty. That is 0.05. Okay, which is about 5 times 10 to the negative 2, which is about 10 to the negative 1. Okay. So it's going to be 10 to the 2 plus minus 10 to the negative 1 kilometers an hour. Okay. 10 to 2 plus minus 10 to negative 1. So you want it in, okay, so this is about the same thing as 10 to the 3 hour. So we want to take this times how many meters are in a mile? No. How many miles are in a meter? So miles over a meter is what? So miles meter. So 1 mile. Okay, 1 mile, 1609 meters. So 1609, that is about 10 to the 3. So these cancel out. Meters cancel out. It's going to be 10. What we're left with, miles an hour. Awesome. Okay, marathon runner completes 42 kilometers. So a marathon runner completes 10 to the 3 kilometers in okay. 10 to the 3 over 2 hours, 30 minutes. So 2.5 hours. Okay, so that's about 10 to the 1 hour. So there is an uncertainty plus minus 10 to the 1 meters plus minus uncertainty of 1 second. 1 second, 10 to 0 seconds. Okay. Calculate the percent uncertainty in the distance. Okay, so we're going to take 10 to the 6 meters divided by I think it's 10 to the 1 divided by 10 to the 6. That can't be right. Percent uncertainty should be, what, 10 to the 1 meters over 10 to the 6 meters times 100%, right? Times 10 to the 2%. So it's going to be 10 to the -5 plus 2, 10 to the -3%. Okay, meters. What is the average speed in meters per second? What is the average speed in meters per second? Okay, so is it 3,600 seconds in an hour? Okay, 3,600 seconds, so there's 10 to the 4. So 10 plus divided by 10, 4 seconds plus minus 10, 0 seconds is about 10 2 meters plus minus 10 to 1 meters per second. Alright, the side of a small rectangular box are measured to be 10 to the 0 times 10 to the -1 area of side 1. Okay, 10 to the 0 times 10 to the -2 equals area of side 2. And 10 to the 0 times -1 equals area side 3. Volume. Okay, so this is plus minus. I'm sorry. Plus minus. Okay. So we want V equals AS 1 to 3. Okay. So that's going to be 10 to the 0 plus minus all right. 85. When a non-metric units, we're using United Kingdom. The unit of measure, a unit of mass called the pound mass was used. Okay, so 1 pound mass equals 10 to the 0. So what is this? 4 times 10 to the negative 1, which is about 10 to the 0. Kilograms. Okay, so if there's an uncertainty of this small amount, so it's 10 to the 0 plus minus 10, 1, 2, 3, 4, 10 to the negative 4 kilograms. Percent uncertainty. So uncertainty, so it's going to be 10 to the negative 4 over 10 to the 0 equals 10 to the negative 4 times 100, or 10 to the 2 equals 10 negative 2%. Okay, so what based on percentage rate? What mass and pound mass? Okay, so that's going to be 10 to the 4 because you add 4 here, you'll get 0. 10 to the 0 is 1. So about 10 to the 4. Um, so being kilograms, we want to convert that into pound mass. So there's 1. Knowing 1. Yeah, 4 kilograms. Awesome. I'm sorry. 10 to the 4. They should be backwards. I'm sorry. So that would be, we want pound mass on bottom, don't we? No, we would want kilograms on bottom. Equals, ten to the 1 pound mass. All right. Length and width of a rectangular room are 10 to the 1 plus Okay, 10 to the 1 plus minus. Calculate area and its uncertainty in square meters. Okay, so the length times width, that's going to be 10 to the 2 plus minus 10 to negative 4 meters area. Okay, next question. Last one. A car engine moves a piston ten to the 1 plus minus 10 to negative 3. Cross section. So what is that? Is that diameter? Okay, yeah, so that's probably diameter equals diameter. So 10 to the 1 plus minus negative 3 centimeters equals distance. By what amount is gas decreased in volume in cubic centimeters? By what amount is the gas decreased in volume? Okay, so we could take this about, so the radius is about the same. So we want to know the area over distance, I think. So that would be 6 times which would be about 10 to the 3 plus minus 10 to the 5 centimeters squared. Divided by this area per distance, 10 to the 1. So it went about 10 to the 2 plus minus 10 to the 8 centimeters. All right. 88. First time bombs ended. 45. This problem challenged you to recreate the famous calculation. From years' experience, Taylor decided the radius r of the fireball should depend only on time since the explosion, t, density of air, rho, and the energy, the initial explosion. So he said r is k e to the a, rho to the b, t to the c. E is meters length squared times squared. Okay, so row density is mass. Okay, and okay, so ABC. So we want to know what these exponents can be. Okay, so we could have, let's say it's e to the 2. It has to all be 0, right? It has to all be, no, it has to all be, k is dimensionless, right? K, okay, so these all have to equal 0. So it's e to the power of something gets you all of these 0. So it would have to be e power 0 would be, but then you're adding them. So, okay, so if we just assume it's like that, then this should be one dimension, right? Just one dimension at a time. So, if E is that, it has to be consistent. So, you could just subtract these, right? So, P, let's see, so P to the negative B would be M1L negative 3. So we need it times, so e to the 6, no, e to the 3, rho to the 2. So that'd be 6, and that'd be 6. Okay. That would be 6. That would be 2. What am I saying? That would be 6, and that would be 6. So these would cancel out. That would be 3. This would be 2. 3. This would be 2. Okay, so can I turn this into a matrix and reduce it to row echelon form? So our solutions are um all right, I give up. Okay, so start by expressing the variables in terms of their dimensions and setting up a dimensionally consistent equation. Radius r is related to time. Let's see, so k e over rho t squared over 1/5. Now we analyze the dimensions of each term. And rho is ml negative 3. So L equals K ml2 t negative 2. I have no idea where they got this equation, by the way. I'll have to ask for an elaboration. Simplifying, so I'm going to try myself. It's going to be L to negative 1. You're supposed to add these, right? So that's 5 over 5. So that'd be 6. 5 over 5. So you multiply where, so that should, this raised to that is multiplying, right? So negative 5 25ths. 5 25ths. Negative So it should just be 1/5, right? Okay, and then so I guess they didn't cancel out. A is 1, B is 2, C is 2/5. The dimensionless constant K has units that now we know the form of the equation, get the data. Converting energy obtained in kilotons of TNT. 1 ton of TNT is approximately 4.2 giga GJs. For the energy in joules, gigajoules divided by this. What is the final answer? uh, Substitute it for me. Alright, so the estimated initial release of the Trinity was approximately 830 kilotons of TNT. Okay, cool story. And I just want to end this chapter, so do this one real quick. Mathematical expression involving physical quantities. You consider the terms of an expression. Mentions. When expressing functions using power series terms, series involve dimensionless constants. Dimensionless, x is the argument of the function, each term in the series is the product. It's because any term raised to the power will have dimensions corresponding to the product of dimensions. We'll argument x have dimensions, and each term in the series would induce different dimensions, and the sum of these terms will not be dimensionless. Therefore, the requirement that all terms in the equation have the same dimension implies that the arguments of standard mathematics must be dimensionless. As a result, it is not necessary to explicitly state this condition separately in the definition of dimensional consistency. Concept of dimensionless constants in the analogy of power series helps to illustrate why the requirement for consistent dimensions is comprehensive in ensuring the overall dimensional consistency of an expression. Okay, that makes sense. All right. Thank you guys for watching. Good progress today. Next time we will pick up with vectors. So have a good one.